Okay, this fourth lecture in Calculus 1, and we'll start talking about subsets, various kind of subsets of the set of real numbers and their different properties. So, in the study of the subsets, is important to have a geometric picture because most of the proofs that we are about to give, once you're able to picture the situation on the real number line, then you can prove it pretty easily, geometrically even. Okay, so that's why we represent this R as this line, right? It extends to plus infinity on the right hand side and minus infinity on the left hand side, and then we take some reference point to be the 0. And once you've plotted your 0, you can plot integers 1, 2, and 3, etc., and -1, -2, -3. And then this, every point on this, so every real number, first of all, can be expressed or can be represented on this line. And so that follows from the decimal expansion of a real number. So once again, we don't have time to talk about all that thing. So, and on the other hand, every single point on this line is going to represent a unique real number. Once again, this is also something that we can't prove in this course. It involves some. So this is a deep result. So I mean, one might wonder why set of all real numbers looks like a straight line without any gaps or anything, right? So so this proof showing that R is actually in fact equal to line. That means every single point on this line is actually a unique real number that requires some deep mathematics, specifically a method called Dedekinds cut. Anyway, so we're going to assume this and move on. So the most important class of example of subsets of R are intervals. So there are mainly two kinds of intervals. You have already come across this before in your high school. The first kind of intervals are bounded. Bounded means they're bounded from both sides. Okay, so so they can be mainly of two different types mainly. So this one is a closed interval, okay, consisting of all real numbers between a and b and including a and b. And you can have an open interval where it consists of all real numbers between a and b excluding a and b, okay, endpoints deleted. Similarly, you can define half open, half closed. These are called clopen intervals. So closed at one end, open at other end, okay. And so throughout, I'm going to use a red dot to denote a point that is a part of the set or the interval, and a blue circle will always denote a point that is to be omitted from the set. And for example, open at B and closed at A will be denoted by this, and it consists of all points in between this. So the symbol I, or the letter I, is reserved to denote an interval, which could be one of these four types, okay, depending on the context. You've already seen this before, and there are some unbounded intervals. So these are not bounded on one of the ends or at both ends, both sides. For example, a infinity is an unbounded interval, so it's bounded from the left, and it consists of all points from A onwards, right? So it's unbounded on the right hand side. Similarly, you have an unbounded open interval. So it's unbounded but closed at A. This one is unbounded but open at A. Similarly, you can have unbounded on the left hand side. So that's going towards minus infinity, and then bounded on the right hand side. Similarly, we have a situation like this. So these are some examples of unbounded intervals. So important examples are R is always represented by this unbounded interval minus infinity to plus. So this includes all real numbers. And notice that throughout, so far, we have always used this, we have never said like, minus infinity with a closed interval sign or plus infinity with a closed interval sign. Why is that? Because moment you use this closed interval sign here, then that means infinity has to be a part of that set, but then infinity becomes a point. So we can't, or in other words, infinity becomes a real number then, right? But infinity is not really a real number. So we always have to keep this open sign whenever your infinity is one of the limits of the interval, okay, or endpoints of the interval. Set of positive reals, set of non-positive reals, they can all be expressed in terms of intervals in this fashion. Another very important example of an interval is a neighborhood. So what is a neighborhood? So neighborhood of a point. So we talk about neighborhood of a point. So in short, I'm going to use NBHD to denote a neighborhood. So if A is a real number, a neighborhood of A is just a symmetric open interval. So about A. So for example, if A is a point on this real number line, and then on either side, I go equal lengths and then form this open interval, A minus H, A plus H. Okay, so H is the amount that I'm going on either side of it. So A belongs to this. So this typically this interval will be called a neighborhood of A. So you can have many neighborhoods of A. So there is no a specific condition on H except that it has to be positive because it's a length that we're traveling on either side, right? So it has to be a positive number. So it can be any positive number. So accordingly, you get infinitely many intervals, neighborhoods of. So a very important class of neighborhoods is the following. So I'm going to call this a sequence of neighborhoods because that's how it's going to look like. So given a point A, we'll look at this neighborhood in, which is formed by going the length of 1 by n on either side of A. So this A plus in, A minus in, okay? And so that gives me a neighborhood. And as n varies, I get a system of neighborhoods. And this particular system has a property that, I1 will contain I2, contain I3, and so on. So such a system is sometimes called a nested system of neighborhoods. Okay, so let's try to look at the picture of such a system of neighborhoods. So given this A, I start with I1 by going a length of 1 on either side. So A plus 1, A minus 1, that gives you I1. Then for n equals to 2, I get a smaller interval containing the first one, A minus half, A plus half. For n equals to 3, I get even a smaller interval, A minus 1/3, A plus 1/3. And I keep doing this and I keep getting smaller and smaller neighborhoods of A. Okay. Next definition is that of a deleted neighborhood. So what is a deleted neighborhood? It's simply, a neighborhood of A with the point A itself being deleted. So this is how. So A minus H, A plus H with the point A deleted. So the central point is being removed from this interval. So I'll use this dash to distinguish from a normal neighborhood. So why do we need these deleted neighborhoods? It's used for, a number of purposes. For example, if I want to study, say, for example, this function fx equals to mod x minus 1 by x minus 1. So on the left-hand side of 1 is minus 1, this function, right? On the right-hand side, it's plus 1, and at x equals to 1, it's undefined. So if I want to say study this function on a neighborhood of 1, then I have this obstruction that I cannot define that neighborhood as its domain because the function is not defined at 1. So I simply consider the deleted neighborhood of 1. So simply delete this point from the neighborhood, then this function becomes well defined on this neighborhood. So this brings us to this next topic, which is a crucial one: distribution of rationals and irrationals on the number line. So in your high school, you have already seen this particular result, that between any two rationals, you can find a third rational. So I'm leaving that as an exercise, assuming everyone. So it's like really a one-step solution to this. So moment you replace these rationals by reals, it becomes, so suppose I want to show that between any two reals, there is a rational number. The method, the one-step method that worked here is definitely not going to work. So, and if you think about it, so before you look at the proof, we just think about it for a second. If there is any obvious method, or an easy method to prove this, you will just using your elementary or high school knowledge, you won't be able to prove this. So here's the main result: between any two real numbers, x and y, with x less than y, I can always find a rational number q. Okay. So I'm going to state a couple of results here that we'll make use of. So when you first look at these results, they will seem really stupid, but the gravity of these results can be, understood by looking at their application. So this, for example, the first result that we're going to use that looks stupid is called the Archimedean property, in short, AP, of positive real numbers. So we'll use it again and again and again. But it's really a simple result. What does it say? It says that if x is a positive number, positive real number, then you can always find a natural number n such that the product nx is bigger than 1. So to many of you, it sounds pretty straightforward, right? I mean, it sounds pretty stupid even, because obviously given any real number, so if I give you some fixed real number, you can always say, if I give you 1 over 100, can you find a natural number n such that when n is multiplied with 1 over 100, you get something that is bigger than 1? Answer is pretty easy. You can simply choose n to be 101. So 101 multiplied by 100, 1 by 100, gives you something bigger than 1. But in mathematics, what happens is you're not working with a fixed real number here. So you're working with an unknown real number x, which is positive, however. So can you argue that for an arbitrary positive real number x, we can always find natural number n such that n is bigger than 1? That's the question. So we have to give some mathematical arguments in order to justify this statement. And the second result is even easier. It says that given any real number x, you can always find an integer n such that x is bigger than or equal to m minus 1 and less than n. Okay. So these are the two observations. So they are so easy. They are so we can call them observations. Okay, so notice that. So this really means that given any x, I can find m such that x belongs to closed at m minus 1 and open at. Okay, so 2 is easier to prove. It's really one-line proof. Let me show you that. So suppose we have this real number, this real number line, and I plot x, or what is that? I plot x here, and I have to find an integer m such that x belongs to m closed interval m minus 1 open interval. Okay, so what am I going to do here? So I plotted my x over here. So I look at, so x has to be strictly less than n. So I look for the integer that is immediately right on the right hand side of x. So notice that this distance, so m by construction, m is the nearest integer to x that is bigger than x. So I'm calling it m. And then obviously m minus 1 is going to be on the left hand side of x. So it's possible that this m minus 1 coincides with x, but I'm saying definitely this m minus 1 is not going to be on the right hand side. So it's not possible that. Why is that? Because m is the nearest integer. So m is the nearest integer to the right of x. And so if, for example, if m minus 1 happens to be on the right hand side of x, that is m minus 1 is strictly bigger than x, then m wouldn't be the nearest one. Then m minus 1 would be the nearest integer to x, right? So that will contradict the choice of m that we are making here. So the moment I make that choice of m, it's immediately clear that this m minus 1 is less than or equal to x. So that proves the first part, or the second result. How about the Archimedean property? So I'm given with, once again, let's recall what's the statement. What is the statement of this Archimedean property is that given any x, positive real number x, I should be able to find a natural number n such that n times x is bigger than 1. So x is a positive real number. It can be bigger than 1, equal to 1, or less than 1. So I'm saying if x is bigger than or equal to 1, this theorem, this result is trivial. So the choice of n is pretty obvious in that. So for example, if x is bigger than 1, then the choice of n is going to be simply, I can simply choose n to be 1. So because 1 times x is then bigger than 1, right? Because x is already bigger than 1. So that takes care of this particular case. If x is equal to 1, I can take n to be 2. Then 2 times 1 is bigger than 1. So we are done. So basically, the interesting case is when x is a positive real number that is less than 1. So how to show that there exists? I can find an x. I can find a natural number n in this case as well. So I look at an example and try to mimic that in my abstract arguments. So I look at x, so x equals to 1 by 3. And suppose I'm given x equals to 1 by 3, how can I get hold of that integer n such that 4 times x or n times x is bigger than 1? I simply choose a natural number n that is bigger than the denominator. So I'm going to proceed in the similar fashion in this, in the case where x is not a given fixed number. Okay, so first of all, I'm saying since x is less than 1, I can write x as 1 by 1 plus h. So you can, so for example, h can be seen to be, so for example, a choice of h, I mean, the unique choice of h here is going to be 1 by x minus 1. See, x is less than 1, therefore 1 by x is strictly bigger than 1. So this quantity is bigger than 0. So x is, so by this identity, x is equal to 1 by 1 plus 1 by x minus 1. I get that. So if we simplify this identity, we get x, right? So I can write x as 1 by 1 plus h. So I've written x as, that looks something similar to 1 by 3. And what did I do then? I chose an integer or natural number that is bigger than this denominator. So I have to choose a natural number that is bigger than 1 plus h, then it will be true. And of course, there are many such choices. So given this 1 plus h, I can choose infinitely many natural numbers that are bigger than them, make it bigger than it, right? Because the set of natural numbers is unbounded. So given any fixed positive number, I can always find infinite. So for example, the choice is here. I'm making a particular choice to make things precise. So this 2 plus floor of h. So this is going to be an integer, and this is an integer which is strictly bigger than 1 plus h. Why is that? Because 2 plus h is 1 plus 1 plus h, and this part is strictly bigger than 1 plus this part is strictly bigger than h, right? Because of this. So h is always in the h is always less than, strictly less than 1 plus h, 1 plus floor h. Okay, and so moment I've made that choice, then nx is strictly bigger than 1 plus h by 1, because n is bigger than 1 plus h, and x is equal to 1 by 1 plus h. So this nx is bigger. Okay, so that was the Archimedean property as well as this other property. Okay, so proof of the theorem. I have to show that given any two real numbers x and y, I can find a rational number between it. So that means I have to find some m by n in between x and y. That means I have to find some m and some integer m and some integer n, with n of course not equal to 0, such that m by n lies between x and y. And here I'm going to make that extra assumption that n is a natural number here. So any rational number can be expressed as an integer over a natural number. For example, if the if you have something like say 3 by 5, then it's clear, right? So only thing we have to worry about is when the rational number is negative. For example, minus 2 by 9. So minus 2 by 9 I can write. So this is actually, I wrote it wrong. So this is minus 2 by 9. So I can write it as minus 2 over 9, right? So that's what I'm doing. So so really I have to find an integer m and a natural number n such that m by n lies between x and y. So I'm calling this inequality star. So how to involve that Archimedean property and the other property here? So to understand or to see how those two results are coming into play, we simplify this expression a little bit. So proving this, showing that m and n exist so that this holds, is same as showing that so n is a natural number, so I can multiply throughout without changing the direction of these inequalities. So that means I have nx less than m less than ny. Then I'm going to subtract nx from each of these expressions to get that 0 less than m minus nx less than n minus x. So showing this is equivalent to showing this, right? Okay, now comes the subtle part. So how are you going to make choices for m and n, and how this Archimedean property comes into the picture? So this is what we're going to do. We're going to show that I can make a choice of m and n such that this m minus nx is positive and less than equal to 1, and n into this expression is strictly bigger than 1. So from this two, if I can show this two, then this will definitely imply a double star. So n into y minus x is strictly bigger than 1, and 1 is bigger than equal to m minus nx. So m minus nx is strictly less than n into y minus x, and m minus nx is positive. Okay. So these two together will imply double star. So all I have to do is find integers m and n such that these two hold. So now you can see how Archimedean property is coming into this picture now. So for example, first I'm going to get hold of this n, and then I'll think about how to find this n. So this choice of n is pretty clear. It's going to come from the Archimedean property. So no matter what x and y were, y is bigger than x, therefore y minus x is a positive real number. So I can find a natural number n such that n into y minus x is bigger than 1. So that's going to be the choice using the Archimedean property. So that's what I'm saying. So once you have made the choice of n, so now n is fixed, x is also fixed or given. So I have to find an m such that m minus nx. So distance between, the distance between m and nx is strictly positive, and it's less than or equal to 1. And now you can already guess how to use the second how the second property is coming to the picture now. Because for this real number nx, I can find, I can put it inside an interval where, which is, so I can find an integer m such that nx is strictly less than m and nx is bigger than or equal to m minus 1. And from this, it follows that m minus nx, so m is strictly bigger than nx, which means m minus nx is strictly positive. So this takes care of this part. And I have to prove that m minus nx is less than or equal to 1. Of course, m minus nx is going to be less than or equal to 1 because distance between m and nx is certainly bounded by a distance between m and m minus 1, right? Because nx is sandwiched in between m minus 1 and m. So this distance cannot exceed 1. So it is less than or equal to 1. So I've found m using the second property and found n using the Archimedean property, where so that this holds, therefore double star holds, and therefore we have found what we want. So we are almost done with this. So your job is to now find a one-line solution to the same problem with the rationals replaced by irrationals. So that means between any two real numbers, there exists an irrational. Okay, that's what to show. So the theorem states that between any two real numbers, there exists one. In fact, I'm saying as a corollary of this, you can in fact show that between any two real numbers, there are infinitely many rationals. Okay, so try to think about how to prove this. Okay, so get used to some abstract thinking. So hint for this one is that if you use this property that between any two real numbers, you can get a rational number again and again. Okay, and the same trick will apply to irrationals as well. So between any two real numbers, you can find infinitely many rationals or irrationals. So as a corollary, we now know that once again, I'm leaving this as an exercise for you to think that if I is an interval, then I contains infinitely many rationals. Okay, once again, it follows from here. Okay, so this is really easy to prove once you know this result. Okay, so think about this, and that'll be it for this class. Next class, we'll start talking about bounded subsets of R. So we've already seen some bounded intervals, but we'll do some general study on bounded subsets and see what that leads us to. Okay, so that will be it.